Up at the top, life is simple. Do one of these, we'll get on with life. For instance, find the value of y when x equals 6, round the answers to the nearest tenth. Let's say we're doing something like 2. Literally, all you're going to do is make sure you get the 6 in there for the exponent. So, when I go to type that in, I'm just going to make sure I get my parentheses with my 1.8, and then I remember my caret to let it know it's an exponent. The only other challenge with this is making sure you're rounding correctly. Okay, we're rounding to 1 decimal place. We're rounding to tenths. So is this going to be 408.1 or 408.2? Okay, 408.1. So again, no big deal. But it's kind of just playing that game of figuring out and kind of being cautious with some things. Okay? No big deal. We kind of skip over the rest of that then. As we move down, again, don't let this kind of throw you for a loop, because some of you, I think, are going to see I and think we're going to start doing interest with imaginary numbers. That'd be kind of interesting, but we're not. Okay, I is just going to be our interest rate in this case. So basically, it's just like what we were just doing in that very last problem. I think it was 66. It's just going to be my principal. 1 plus my rate. Then the time is going to be here. And again, straightforward, knock it out, get an answer out. Make sure your answer is sensible. Like here, if I'm getting 4% interest for 8 years, like if I get an answer like I'm getting $4,000, yeah, that's not sensible. So it kind of, doing problems like this is just going to make sure that I'm paying close attention to detail stuff. Okay, that's sensible over 8 years. You know, I should have some more money. 28 cents. Shouldn't be a load of money, because we found out yesterday money can be in an account for like 20 years, and it takes that to double sometimes. So here that'd take quite a while. So this is sensible. On one like that, I'm not going to worry about it as much. No, I wouldn't worry about it. As long as you're getting the answers that look correct, that's okay on me. So then, we kind of start getting into some actual applications of things. Now again, there's not that big of a difference between 15 and what we were just doing up above. It's just now here's a word problem that goes with it. The frequency of notes on a piano can be modeled by this equation. Okay? It's just they did the plus part for us already. Instead of being 1 plus 0.06, it's actually in its form already. So middle E, which is 7 half steps above low A, use 7 for x, get an answer out your frequency. So all I'm doing, again, would be plugging that in for x and getting an answer out to figure out the frequency. The key, again, is just reading carefully. The work itself isn't bad. It's just actually saying, okay, I got to actually take a moment here to make sure I'm getting things that are sensible. Oops. Then I'm not typing in the wrong numbers. And again, on any of these, if you don't see anything saying anything different, we're just going to round to tenths. That way we're all doing the same thing. So again, nothing terrible. Then it starts to get a little more interesting. Even though I'm giving you hints on what to type in for some of the things, I want you to know how to build this yourself. Because when we get to equations, I have to be able to build. So for instance, here, if I jump down to 16, see 17 will be similar, we'll kind of just take a peek. It's estimated that in 1995 there were 2 million mice living in Jellystone Park. A lethal disease was introduced into the area, and each month half of the mice die. Find the number of mice each month. Now I know you're capable of just doing divide by 2, divide by 2, divide by 2. But let's think about this for a minute. My initial amount, or principal, not really principal, we're not talking about money here, is going to be 2 million. If they're dying each month, is that growth or decay? Decay. So it's going to be 1 minus, what's my rate of decay? Okay, 0.5, half of them are dying. Okay, times however long that is. That would be my expression for this. Right, so each month then would just be replacing this. Now in this case, since we want it for like 1, 2, 3, 4, 5, and 10, I wouldn't keep retyping this in each time for those. Shoot, that's going to take a while. It's great if I only wanted one of them. So my suggestion here would be to go back into the graphing portion and type it in. Just go into the y equals. And again, I'm just going to use x for my exponent. And again, this is going to allow me, when I go to the table, so once I get it typed in, I'm not even going to bother going to the graph. I'm just going to hit the second graph to get to the table. What I can start doing is, I can go, okay, I'll go back to y equals for a minute and see if I did something really weird. Why am I skipping a year? So, should be going down to half that. Why isn't it going? Now, some of you are probably noticing the same thing I am. Everything has been shifted off by 1. Because my 1 should be 500,000, because half of them die off. Oh, duh, Hardy, what are you doing? 1e to the 6th. This is where some of those things come in sometimes. Actually, I'm going to write it on here, because you can see it and see it. 1e to the 6th means 1 times 10 to the 6th, which is, 1 million, which is exactly what I want it to be. Oh, boy. I know, sometimes the calculator's just proven in this case it's smarter than I am. So, and then it's going to keep going down each month by another half. So instead of having to type something like this in, I can just keep going back to the calculator and just jotting down what I see in the chart until it turns itself off. Now, even though I mentioned down when you get to the 10th month, type this into the calculator, I could, again, 1 minus a half is where this half would be coming from, but if I can just put it into the chart, and instead of doing that, go down to 10, and get to the solution, why not? Okay? I can knock 6 answers out really quick instead of having to retype it for every single one. And again, 17 would be the same idea, and I'm just going to set up their initial equation. If my new Jeep costs $36,000, each year it depreciates and is only worth 90% of the previous year's value. Okay? Sometimes they'll actually tell you what it is. This time they're going to tell me, instead of me having to do 1 minus, it's 90%. So if they literally tell you what it is, you can just use that number. So sometimes they'll tell you the value, sometimes they'll tell you what that growth or decay rate is, and you'll have to do it. But again, type this in your graphing portion in the y equals, and that'll end up making this work out for you that way. And then that would work throughout that chart. And again, just kind of getting into the thought process so when some of these twists are coming at you on an assignment, you can get through them. just a couple last things to take a peek at, and I'm going to kind of set you off here. Okay, up at the top, again, just finding values and rounding, you're more than capable of that. So I'm not going to worry about playing with that very much. 9 is one that I want to take a look at, though. This is the one on the back we need to look a little deeper at. There's some information here that we have to calculate. So on 9, it says the population of Akron decreased from 237,177 in 1980 to 223,019 in 1990. By what percent did the population drop? When you're doing this, okay, you need to find the difference that they have. So in this case, I would subtract bigger minus smaller. So subtract the two values. And we're always dividing by the original value to find the rate. So it's the difference divided by whatever our original amount. Whether it's money, whether it's population, whatever it is how we're going to set this up. So once I do this, and again, I can type that into the calculator. If you go straight to the calculator and want to do it all at once, make sure you use parentheses up top, because otherwise you're going to be in for a surprise. And again, whatever that percentage is, in this case, it may even be a good idea to just leave it in its decimal form. Now I know that's not the percentage. The percentage itself would be 5.97, okay? But think about what we're going to be using it for. Suppose the population continues to drop by that same percentage in the future decades. Write an equation that models it. Drop is going to be like decay. So I'd have my base model. Okay, my base model is always my original. What did I start with? Well, in 1980, I started with 237,177 people. Since it's dropping, it's going to be decay. So 1 minus that 5.97% over the amount of time. So here would be my question. It started in 1980. We're going by decades. I want to know what the population will be in 2030. What t-value would I want? But we're going by decade, not by year. 5. It's another one of those kind of things that keeps talking about in future decades. So if you start at 1980, you're not counting by single years. You're counting by 10-year periods. So it's one of those things, sometimes they may count by years, sometimes they may count by minutes, sometimes it may be decades. You have to watch for that. Because if you'd have typed in 50, oh my gosh, you'd have been looking at 500 years later. Oops, I'm going way too far. My base year is always going to be 0. And then we just add 1 after that each time. So my t-value here would be 5. Now, since I'm only looking for it once, I probably would just type this in as an equation and put t in for 5 and get my answer out, which I believe... Okay, let's see what's going on here. So I've got... Alright, let's get out of here. I'm just going to type it in. Since I only need 1, I'll just put in 1. 7. And again, since I want it for year 5, looks like we'd have about 174,343 people living in Akron in 2030. And again, there's little things that can get you there. Let's say you forget the 0 here. and you put in 0.597. Well, now it's decreasing by 60% every year. There may nobody be living in Akron by 2030, possibly. Very few people in the end of the world, yeah, like mine. So that's what we're looking at here, okay? The sheet that you've got for today, or you can kind of keep working back with some of the other ones if you so